Okay, good morning, students. It's good to be back. It's good to be back in the game. I haven't had a lot of engagement with you guys since last semester and the final. So it's good to be back. Look forward to seeing you guys again. Also look forward to lecturing you guys now for the semester for refrigeration 3 as it's called, but essentially thermodynamics 3. Yeah, so let's get going. I'm assuming everyone can see the slide. Can someone just confirm?
Yes, sir, it's visible.
Okay. Can you see the next one? It says lectures.
Positive, sir.
Okay, fantastic. So basically, our lecture is going to be conducted for the semester. For now, we'll be using this platform you basically on now, Blackboard Collaborate. Now it's going to be conducted. A link will be sent to you before the lecture begins, like 15 to 20 minutes before. And of course, the third point is on-campus lectures. They're still under discussion. I'm not aware exactly what's the discussion in terms of how they're gonna facilitate all the students, but I know the HODs have to meet the hotel school and Ms. Williams and basically decide on how we're gonna schedule the thing. I did see something in terms of like 1 week you allow the students coming on board, and then the next week, but it's like a rotational 2-week thing. But like I said, that's still being decided. So yeah, so basically lectures will be on this platform. This will also be done for electrotechnology 3 and stencil materials 3, well, which is titled maintenance engineering. So yeah, so it's okay, cool. Next slide. Okay, so for the subject, the prescribed textbook is Eunice Engel and Michael Bowles. It's thermodynamics engineering approach. It's a thick textbook. I'm not sure if you guys have seen it before. Is anyone familiar with this textbook? Hello?
No, sir, I don't think so.
Okay, so I'll share, just give me a second. I just want to share you how the cover looks so everyone can see. Just give me a second. Let me just share the screen over here. Stop sharing that. Okay. Can you guys see it now? Can you guys see it? You should be able to see it. Fantastic. So that's the book, right? Thanks. You can get either the 8th edition or the 9th. In fact, even the 7th is fine. So that's the textbook we're going to be using for the semester. So let me just get back to the slides quickly. I also recommend eStop and McConkey Applied Thermodynamics for Engineering for Technologists. It's a very good book as well. I'll probably be leveraging onto it. What I do recommend is for the textbooks, we'll discuss on WhatsApp on your approach on how to get them. You can either purchase them via Skype or any bookstore or online, but it's very good textbooks to have, not only for the subject, but for your career as a whole. It's a concrete textbook, Eunice Engel. So yeah, that's the thing we'll be using. It has a lot of exercises, detailed explanations and how things work. So it's a really fantastic textbook. Okay, so let's move on to the next slide now. Okay, so for refrigeration 3, as its title, there'll be 8 sections being covered. You'll be looking at gas-powered cycles, or essentially basically using gas to provide power to systems. We're looking at internal combustion engines, which is basically your petrol engines, which runs on an Otto cycle. Looking at the diesel and the dual cycle as well. And then we'll also be looking at basically engine testing performance. So we'll be looking at different metrics. When testing an engine, we're discussing different test methods. And then after that, we're still on gas power cycles. We'll be looking at the Brayton cycle, also well, layman's call it the dual cycle. That's essentially external combustion engine, and we're looking how gas turbines, we can all the thermodynamics behind the gas turbines. And then I think, yes, and then after that, that'll be steam cycles, which is vapor or two-phase cycles. You'll be looking at essentially the Rankine cycle, if you guys remember, but there'll be additions on it. We're looking at the reheat and regenerative supplements to it to improve the efficiency. How can we improve the efficiency? We can play around with that. Then we come to refrigeration. We're looking at all refrigeration, the ideal actual cycles, how it works, the vapor compression cycle in detail, and we also look at cascade cycles. That's basically two stages of refrigeration cycles on top of each other in cascade. We look at some air conditioning, look at psychometry. You'll be learning about humidity, your wet bulb, dry bulb. I'm not sure if you guys are aware of these concepts. We're looking at basically air conditioning, its mechanisms. Then we go into heat transfer, and you'll be looking at a few things over there. We'll be looking at heat conduction, convection, and iteration. We'll be looking at through different objects, or we'll be looking through pipes, heat transfer through pipes, through walls. We might go into heat exchanges depending on time. After that, we'll be looking at reciprocating air compressors. Yes, you've probably seen an air compressor before at home, so we'll be looking at the thermodynamics involved in that for both single stage and double stage. And then finally, we're ending off combustion, and we can basically find out. Can you guys see my screen? I'm not sure what happened. Okay, cool. Yeah. And then combustion. So basically, you're going to work out how to find the optimum air needed for combustion. You can work out as well your I don't know if you remember your calorific values, your lower and higher ones, the mathematical modeling behind all of that. So yeah, it's a bit of work. And the way I wanted to view this subject particularly as essentially applied thermodynamics for the most part. So it's the things we've learned, and then we're essentially applying all these things to cycles. So how we essentially use heat, and we are able to convert the heat into work. So that's what essentially the whole subject is about. Okay, next slide. Okay, so guys, this is my discussion. Your first test will be between that period, according to the academic calendar dates. I'm not sure if this is all. Excuse me. I'm not sure if this is all concrete or tentative, but that's when you write your first test. Of course, it'll weigh 50%, as you know it. Now, I'd like to discuss test 2. Would you guys like another test, or would you guys like some variation in terms of assessments? Someone can raise their hand and basically give me some of their thoughts. It's open for discussion, so please let me know. I'm waiting on someone. Mr. Naidu.
Sir, just a question. What do you mean by variation, assessment variation?
Fantastic. So what I mean is that, for instance, for the test 2 mark, right, as I call it, with quotation marks, we could split up that 15 to 20, 20 or 10 or 20, 30. So variation mean I might give a research assignment. We allow you guys to research, you know. I might give you a journal article or scientific paper essentially. And I'd like to get specific informations from that. Yeah. So it'll be cutting edge stuff like maybe using biodiesel within a ship, a diesel engine essentially, right? In a marine application. I might ask several questions on that. That's an example of a research assignment. Variation also, another variation would be I have an Excel spreadsheet where you guys can develop. So you guys are able to play around in the Excel spreadsheet, create one, basically modeling a cycle. I'll get into it as we start the subject, and then also maybe small online tests. So maybe 3, you know, like a test with 3 questions, or you could say like tutorials, if one could put it. So that's what I mean by variation. So it's either all these smaller things or one big test. You know, if you're with me, Insa. Is that clear?
Yes, sir. It's much clear. I think that would work out better.
Okay, so what do you guys think? Maybe I should start a poll or something, yeah? Mr. Lise or Mr. Malema, if I should call you. I'll just give me a second. I don't know if you guys will see the poll. So just give me a second. I'll start the poll now. Okay. I think the poll's out. Let's have a look. Yes, Brandon, you can use a J. Lee's textbook. That'll be sufficient for revision. I do highly recommend it. So yeah, I don't know if you guys can see the poll. Well, I can see it. Okay, so it looks like it's leaning towards yes, which is fantastic. Just waiting for everyone to respond. 17, no responses. Okay, it's decreasing now. Yeah, basically it's gonna be. Can everyone see the poll and the results? Hello? Leletu? Gugu? Miss Mata? Can you guys see the poll's results?
Yes, sir, we
Fantastic.
can. We just, yeah.
Oh, cool. Cool, that's fine. Okay, yeah, well, we'll give it like a minute left. But essentially into yes, it would make a difference at this stage. And if people are not here, they unfortunately can't poll this. So you have a variation of assessments, so that is fantastic. I guess everyone's happy with that, yeah. Okay, cool. So we can move on. So your first test, so we can get back onto the presentation. I'll just close this guy up. Yeah, and then our final mark will be written. The FISA or the final examination will be the externally moderated exam will be written between the 30th of November and 11th of December. I'm not sure. It might be a week. It might start in the start the first week of December. I've seen different dates. So yeah. I'm not exactly sure then, but it's within that period. It's a bit disastrous for all of us, but anyway, cool. Next slide. Okay, so I'll start on some revision, guys. I'm missing something else here. One of my slides not here. Okay, no, it's fine. The next slide was essentially the semester plan, but it's okay. I can show that again. So I'd like to get started with the lecture. You know, I don't have time to mess around. So this is what's going to be expected from you. Mr. Msa, you're raising your hand. Okay, or maybe not. Yeah, so revision. So I know some of you guys did thermos 2 with me. I hope you guys remember. I know it's a bit of a jump now. I should have warned you for that now, but anyway. What's required for you for the specific subject, it's very important, is that you know your laws, right? Boyle's law, Charles' law, or Monton's law, and of course the combined gas law, or also known as the equation of state. I will be posting a document with a summary of all of this, but I'll just briefly go over them. Law is essentially when they fix the mass and temperature, and then they look at the relationship between pressure and volume. And of course, that they find that the volume was inversely proportional to pressure. So what it means, if the pressure goes up, the volume decreases. And if the volume goes up, the pressure decreases. So it's that kind of relationship. So that was Boyle's law. So then Charles developed something similar, but in this case, he kept the pressure constant and the mass. N is normally represent the mass, or you could say the number of moles, maybe. You could say maybe. And when he did that experiments, he found that when you increase the volume, the temperature increases, they're directly proportional, and then likewise when they decrease. So that's really interesting. Oh, am I lying here? It feels like I am. Anyway, then the Monton's law, essentially they keep the volume constant, and then likewise on the mass, and they pick up a relationship between pressure and temperature. So that's the important things to know. And eventually, all the 3 laws are combined into the equation of state, which is PV over T. This is all for an ideal gas, not for a real gas. To model a real gas, it's a bit complicated. I can show you that later on in the subject, but for us, we're just dealing with ideal gases. Okay, so next slide. Cool. Just a few things to note. If you guys remember, if you look at the first box over here, this over here, so I can get my, just give me a second. Just wanna be able to maybe can actually do it. Cool. Yeah. So if you have a look at the first the introduction part where it says 5.1, it talks about essentially the gas laws, and they are governed by 2 principles, right? But essentially the 2 laws of thermodynamics, and they are based on the principle of energy conservation, and we'll be applying it to 7 different methods of heating and expanding. I don't know if you guys remember this. I hope you do. What's very important about this, the gas laws, this is only for a closed system. So we assume that no mass is escaping or moving through a boundary, right? So it's closed. So this could be, for an example, what we'll be seeing, a piston, well, in a piston chamber, when we have the air fuel mixture and basically combusts. So it's an example of a closed system, right? It's essentially, look at the picture over there, heat Q12, or the heat being supplied, that could come from the combustion. That pushes the piston down to point 2, and that's how we generate work. So it's essentially looking at closed systems, and it's governed by the first law, the non-steady flow equation, where the heat is equal to the internal energy plus work. Now, these are terms we can go over eventually over time, but it's, of course, this is your homework. It's Thermos 2. If you have these questions, I can always go over them again, prepare a small lecture for them. So it's important, if you look to your right now, sorry, that's what left, right. Basically, this gives you all the equations you need to know for each processes, right? So there's a constant pressure process, the constant volume process, the constant temperature process, the adiabatic process or reversible adiabatic, also the polytropic. So those are essentially the 5 heating, expanding, and compressive methods, which you kind of have to go over. All of these will be applying to all the cycles. And then going back to this guy over here, this is where it's also important to note certain conventions. So when we achieve a work greater than 0, it's called expanding. And when work is less than 0, it's considered compression. When internal energy is greater, there's an increase in internal energy, and the internal energy decrease. Well, it's less than 0, it's decrease in energy. Likewise with the heat, and likewise with the heat, whether it's greater than 0 or less than 0, whether it's gained or lost. So these are just, we're going to go over a few questions of this, so don't worry. So I'm just making you aware, this is something you got to do until next week. Make sure you know your gas laws and heating of gases back to front, because all of those will be applied to ICEs essentially, and both the Otto cycle, Teasel cycle, and the Tube cycle. Okay, is everyone with me so far? Fantastic, right? That is some backdrop. Okay, so what I recommend now is you crack out a book and a pen. I'll give everyone 3 minutes till 9:45, and then we can start solving. We'll basically be doing some questions on the heating of gases. So yeah, that's what we're going to be doing now. So by 9:45, we'll proceed with the lecture. All right, is everyone ready? Hello? Fantastic. Where am I here? Okay, so give me a second. Let's see if my pen works. Can everyone see the question? Okay, great. So let's get cracking. Undo this. Okay, cool. So the question goes, a rigid container holds 1 kilogram of air, initially at 4.8 bar and 150 degrees, right? So you've got a container and it's holding some air at 150. So now the air is heated until its temperature is 200. Determine a few things over there. So the first thing, when you approach these questions, right, first you have to identify the process. What process is this? Can someone tell me? And why do you think it is?
Constant volume process, sir.
Fantastic, Mr. Nidus. Good to hear you speak.
Because rigid
Yes,
container,
I think
sir.
you're breaking up. What did you say? Mr. Naidu, you said something.
No, sir. Nothing.
Yeah, it's constant volume, right? Keyword here, rigid. Is that okay? Okay, cool. So, just want to get that right here. So that's the first thing, right? So you have to identify which process it is. The next thing I normally do, and I call this at number 2, is I write down my non-flow energy equation, right? This tells me this equation applies to all processes. So in the case of a constant volume process, right? What is important to note is that there is no work being done. Do we all understand that? So we have air and there's basically heat being supplied. So we're not using the gas for any work. So we know that the work is equal to 0. So therefore, Q will be equal to the internal energy. Cool. Is everyone happy with that? Okay, so first question here, right? It says, let me just undo all of this for more space. So that's important. I'll just undo all of that so you can actually solve the question. Let me just erase this. All. Cool. Fantastic. Okay, so how do we compute the final air pressure? Can someone give me a sign? How do I start? Anyone?
T1 over T2 is equal to T1 over T2 is equal to P1 over P2.
Okay, so essentially this is the way I do it. Next thing is write the equation of state down. It's P1 state before over state afterwards. This is actually Mr. Naidu basically said in a different way. But in this case, the volume is constant, right? So there we just left with P1 over T1, P2 over P1. Does it make sense to everyone? Can someone just say yes, please? You guys can talk.
Yes, sir.
Fantastic. Okay. So at the first state, right, we have 4.8 bar. So we assume in our case that 1 bar is equal to 100 kPa, right? So in this case, this is going to be 4.8 times 100 kilopascals divided by what? Who can tell me? Who remembers?
You must change the temperature to Kelvin, sir.
Mr. Naidu, what are you smoking? You're too sharp, man. Fantastic. So that's 200 plus 273. Fantastic, right? And then this will be equal to P2, which is the variable of question. And then we know after 200, oh, sorry, this is incorrect here. Let me go back. This should be 150. This is the initial temperature. And this is the final one. So that's 200 plus 273. Okay, cool. So we can work this out. Let me just open my calculator quickly. Then I'll express this as P2. So P2 will be equal to 4.8 times 100 kilopascals divided by 150 plus 273 multiplied by 200 times 273. My question to you is, what do you think the pressure will be? Will it be higher or lower? Can someone tell me, please? Or should I create a poll for this? What will the pressure be, guys? Remember the 3 laws: Charles' law, Bohr's law, Montan's law. Okay, I guess no one's feeling confident today. Let's see here. You should get Yakuza higher. I'd like to know why shortly. Just give me a second. So let's see if you all get the same answer. You all see the calculator, guys? Students? Can we all see the calculator? Yes. Okay, no response again. Yeah, that's the answer. You should get 536.74. Is that correct? Yes, fantastic. That's it. High temperature causes an increase in temperature on Montan's law. That's fantastic. So let's go back to our where is it now? Just give me a second. So the answer should be 5 it's 576.74. Sorry, 536, sorry. And that's in kilopascals. Cool. So is everyone happy with that? Yeah, cool. Mbo, speak to me, guys.
Yes, sir.
Fantastic. Okay, so that's A, right? B, they ask, is their work done? Like I said before, if you look at your non-flow equation, there is no work done in a constant volume process. Very important. Be very vigilant of such things. Right? So hence that answer 0 over here. The answers are given at the end. Okay. Next part of the question. The change in internal energy. This can be calculated by mass times CV times T2 minus T1. So always remember, internal energy is always, you always have to use your constant volume heat capacity. And I'll explain to you again why. For change in U. Always use your constant volume heat capacity, not CP, CV. So in this case, we had 1 kilogram of air. As stated, it's not worth writing. CV in this case would be 0.718 kilojoules or 718 joules per kilogram Kelvin. And our change in temperature was 200 minus 150. Your temperature could either be in Kelvin or degrees Celsius. It should all work out to the same answer. What do we get over here? What do you guys get? 35.9. .9 kilojoules, right? Not per kilogram because we had one kilogram of mass, 1 kilogram of air. Okay. And then last question is D, the heat supplied, and basically D is also equal to 35.9 kilojoules as according to the non-flow steady equation. So if we cancel out that guy, Q is equal to the change in internal energy. And what's important to note for all these questions, I want to make you aware of something. We should state whether heat was gained or lost. In this case, heat was gained. Right? This is very important because it makes sense that heat was gained as a temperature, increase in temperature was applicable. And also there's an increase in internal energy, likewise, due to the positive sign. Okay, guys, it's 10 o'clock now. I hope you guys enjoyed the first intro. I hope it was all positive. We can have a chat for 5 minutes. Well, I don't know if you have a next lecture, and then I'll meet with you guys again 10 to 12, and I'll be uploading everything then. So is everyone fine with that? How did you guys find that? Kieran, Ms. Kumbi, Ms. Tuba, Chauke, Mr. Parao.
Removing some rust.
Excuse me?
We are removing some rust.
Oh no, I know, don't worry. I know. I'm here to take care of that rust just for this, just for today, just for this week. Shane, how are you doing? Is it dark? Is it
Good, sir. Just to refreshen up a bit, man. Just get
Okay.
the brain cells going from a couple of years back.
Okay, no, that's fantastic. That's why I thought I would do an introduction to this. So guys, it's fine if we spend the rest of the next lecture on revision, or should I go into the good stuff? Mr. Lecoq, what do you think?
So let's keep the revision till we get the books and stuff.
Okay, fantastic. Okay. Proudest. Oh, don't dump the steam tables too quickly. No, Kieran, man. Kugu, yes. Okay, guys, fantastic, man. It was great hearing you guys. Yes, the books. We'll sort out the books. Don't worry. Tell me, do you guys have lectures in between now and when I see you? Or when I have lectures again?
So you're the only lecturer that has communicated with us about lectures today. Other
Yes.
than that, we have no idea what's happening. So
I
as
see.
far as we know, it's only you now and you at 12 o'clock. That's all
Yeah,
we know
okay.
so far.
I hope I didn't impede on you guys' holiday. You know, I wasn't too sure. I didn't want to take a chance, man. You know? I just thought I could you guys going at least with the revision to start off with, because I mean, I
So they
forget about
did
it.
tell us that you are starting lectures this week, but we
see.
haven't gotten any feedback from anyone else besides you.
Okay, thanks, Shane. Thanks, Loreto. Okay, guys, I'm not sure it's the same link, but I'll just repost if I'm not sure again. So don't worry. So, guys, thanks again. It's nice to hear from you guys. Yeah, I'll post the stuff in the next 15 minutes. Just want to grab a coffee, and then you guys can start practicing. So are we going to use WhatsApp group for thermos communications? Yes, we'll be using the group as per normal. Guys, you know me, I'm always on the group. Just give me a shout. Just be patient with me. Okay, guys, thanks. I will stop recording the session, and yeah, I'll see you in the next hour, 2 hours. Okay, cheers.